On the night of February 25, 2019, concrete trucks started arriving every 90 seconds at a stretch of open desert 45 kilometers east of Cairo, and they didn't stop for the next 38 hours straight. That is roughly half the time the job was originally scheduled to take. Engineers on the project had openly doubted that a foundation this size could even be poured as one continuous piece, and more than a few had doubted the ground itself, loose desert sand sitting on a layer of basalt rock, could carry what was coming. This is the iconic tower, and nearly 5 years after it topped out as the tallest building on the African continent, there is still no way to know how it behaves over the next 50 years, because nothing built quite like it has been standing anywhere near that long. The tower exists because Egypt wanted a new capital, and a new capital needs a skyline. President Abdel Fattah el-Sisi announced the plan for the new administrative capital in March 2015, a government-led megaproject meant to pull Egypt's political and financial center out of a Cairo choking on 23 million people and rebuild it from bare sand, 45 kilometers east. The brief went to Dar al-Handasa Share and Partners, a Beirut-founded architecture and engineering firm with its design center in Cairo, working alongside its sister company Perkins and Will. The design brief wasn't subtle: give the new capital a single building the whole world would recognize. Dar's designers shaped the tower like a pharaonic obelisk and wrapped it in a glass crown meant to echo the twin-feather headdress of the god Ammonius. This was never framed as an engineering challenge. It was framed as a flag, and by most measures, it delivered. The iconic tower stands 393.8 meters tall, 77 floors of office space, a 5-star hotel, and residences, wrapped around 265,000 square meters of floor area. When it topped out at full height on August 24, 2021, it became the tallest structure in Africa, clearing South Africa's Leonardo Tower by close to 160 meters and overtaking Algeria's Great Mosque minaret as the continent's record holder once construction finished in 2024. Workers put up the steel frame at a rate of roughly one floor every 3 to 4 days, using around 18,000 tons of steel, some single components weighing 28 tons apiece. Cohn won the contract to fit 60 custom elevators and escalators inside it. On paper, this is a finished, functioning, record-setting supertall. Genuinely impressive. Honestly, a little startling how fast it went up. In theory, because before any of that steel went in, the ground underneath had to solve a problem nobody could design around. The soil at the site was some of the softest in the region, and there was no way a tower this heavy was standing on it directly. Here's the thing about soft desert soil that every geotechnical engineer knows. In a normal building, the foundation spreads the load across soil that's dense enough to carry it without shifting much, and the concrete underneath cures in relatively thin layers, losing its heat to the air about as fast as it generates it. The moment you're building Africa's first supertall on loose desert sand, everything changes. The engineers went down to a layer of basalt rock beneath the sand and decided to set the whole tower's raft foundation directly onto it. A single reinforced concrete slab designed to spread nearly 400 meters of building weight across a wide enough footprint that the rock, not the sand, does the holding. But that raft itself created a second problem, one most people never think about: mass concrete. Pour concrete in a slab this thick, 5 meters deep, 18,500 cubic meters in volume, and the cement inside doesn't cure quietly. It generates heat as a chemical byproduct of hardening, called the heat of hydration. In a normal pour, that heat escapes into the air almost as fast as it builds. In a mass pour this size, the core can trap heat far faster than the surface can shed it, and if the gap between the hot interior and the cooling exterior gets too wide, the slab tears itself apart from thermal stress before it even finishes curing.
Let's talk about what happens structurally when you try to solve that at this scale. Dar's engineers weighed pouring the raft in stages, with construction joints between them, the standard, lower-risk approach. They rejected it. A raft this size, poured in sections, would leave seams, weak planes running straight through the one component holding the entire tower's weight. So they chose the harder option, one continuous pour, no joints, the whole 18,500 cubic meters as a single piece, and then had to engineer their way around the heat problem that decision created. They built a 5 by 5 by 5 meter concrete mock-up first, buried it with temperature sensors, and measured exactly how hot the core would get. They specified a cement blend, CEM2 with silica fume added, chosen specifically to slow the heat buildup, and tuned the mix to hold an 11-hour setting window, long enough to keep the whole pour flowing as one continuous mass without a cold seam forming anywhere inside it. Then they brought in a pumping system built to move concrete at 785 cubic meters an hour, 4 to 5 times the rate a normal pour would need. The steel reinforcement alone came to 4,600 tons, threaded through the raft at a density of 250 kilograms for every cubic meter of concrete. Every part of that plant existed to answer one question: how do you pour something this massive without it cracking itself apart from the inside before it ever holds a single floor? But here's something about this building that nobody ever explains, because it isn't dramatic enough for a headline. Once you've solved the foundation, you've only solved the part of the tower that sits still. Everything above it moves, and it moves at different speeds depending on what's inside it. The iconic tower stacks offices, a hotel, and residences in the same structural frame, and each of those has a different sustained load sitting on its columns day to day. Office floors, hotel floors, and residential floors compress under their own weight at slightly different rates over time, a phenomenon structural engineers call differential column shortening. And on a mixed-use super tall, floors that started level can drift out of alignment by measurable amounts over the decades, enough that door frames, elevator rails, and curtain wall joints all have to be engineered with room to absorb it. And this part barely gets mentioned anywhere. 60 elevators moving through nearly 400 meters of a building that sways slightly in the wind and expands and contracts with the heat need rail systems and cable slack built specifically to tolerate that motion. Or the ride stops being smooth and starts being a maintenance problem. None of it is a flaw. It's just the unglamorous, ongoing arithmetic of keeping a very tall, very hot building usable. The clearest evidence of how tightly this project was run against the clock is the raft pour itself on February 25th and 26th, 2019. Within the first 2 hours, batch plants across the site were running continuously, feeding a convoy of transit mixers arriving on a schedule measured in minutes, not hours. Within 12 hours, the pumping system was holding close to its rated 785 cubic meters an hour, with temperature sensors buried in the fresh concrete streaming readings back to the site engineers in real time, watching for any sign the core was outrunning its planned cooling curve. Within 24 hours, more than half of the 18,500 cubic meters was in place, and the retaining wall built in place of formwork was holding under a load it had been designed for exactly once. By hour 38, the entire raft was complete, poured as a single unbroken mass, roughly half the 72 hours the job had originally been budgeted for. Egyptian Prime Minister Mustafa Madbouly, who watched the final pour, called it a miracle by all means. Nobody was hurt. Nothing failed. It is, on the record, one of the cleanest examples of a high-risk mass pour going exactly to plan. Here is the fundamental difference between the iconic tower and every other super tall we've covered. Boston's John Hancock Tower spent the early 1970s shedding 4 by 11-foot glass panels onto the sidewalk below, a well-documented failure traced to a flawed window design under thermal and wind stress. A building that failed in public, in real time, with a paper trail. New York City Corp Center spent 1978 undergoing secret night shift welding after its own structural engineer, William Lemessurier, realized the tower's bolted joints couldn't survive a strong quartering wind, a near miss caught and fixed before anyone outside the project even knew. Even the Burj Khalifa has decades of published creep and settlement data now, because engineers have been measuring it since before it opened. The iconic tower has none of that. Not a documented crack, not a near miss, not a published anomaly of any kind. What it has instead is an absence, because it simply hasn't been standing long enough for a failure, a near miss, or even a slow, boring settlement curve to show up in anyone's data yet. And that absence is the actual story here. Concrete doesn't stop changing once it cures. It creeps, slowly deforming under sustained load, and it shrinks in tiny increments for years after the pour. A raft this size, sitting on basalt bedrock in a location that swings through some of the widest daily temperature ranges any super tall foundation has ever been asked to sit through, expands and contracts on a cycle no engineer designed from a 50-year dataset, because that dataset doesn't exist. There is no historical data for what a monolithic raft this size looks like at 50 years, cast in one piece on desert basalt, because no foundation like it is 50 years old. This is the first. It is the only one. Fast forward to 2074, and there will be a structural inspection team somewhere in Egypt pulling sensor logs and settlement readings off a foundation that, right now, exists only as a plan and a 38-hour pour on video. What they find will be the first real answer to a question nobody currently has the years on record to ask. None of that is on anyone's mind at street level. Civil servants have been relocating to ministries in the new administrative capital for several years now, part of a government planned population target of 6.5 million residents by 2050. Hotel guests check in dozens of floors above the raft and never think about basalt. Tourists come specifically to photograph the tallest building on the continent, the way people once traveled to see the Burj Khalifa. And workers who poured that raft back in February 2019 still talk about the noise of the pumps running non-stop for a night and a day and a night again. None of them are thinking about what a 50-year-old raft foundation is supposed to look like, because as of right now, nobody on Earth can tell them. Somewhere at an office on floor 40 right now, someone is waiting for an elevator, checking their phone, thinking about lunch, not about basalt, not about heat of hydration, not about the fact that they're standing in the only building of its kind old enough to almost, but not quite, start generating the data that will tell engineers 50 years from now whether every decision made on that February night in 2019 was as sound as it looked. Would you take an office on the 40th floor of a building this young, on a foundation nobody's ever watched age? See you in the next one!